Hello again from Digicool Things. The interrupt inputs on our CPU card trigger initiating an interrupt service routine on the processor either during a negative transition or when a low level is applied to the relevant interrupt input. On the Minimalist Europe Card Bus, we bring out both the common maskable interrupt input, INT, as well as the non-maskable interrupt input, NMI. As an interrupt signal can originate from multiple sources, it's normal for this bus signal to be pulled high with a pull-up resistor at the CPU, and any connection to the interrupt input is then only made via either an open collector or an open drain driver. So you never drive the interrupt input high. This avoids any conflict with other devices also connected to the interrupt input. Connecting a positive logic signal to the active low interrupt input of a retro TTL level system commonly involves the use of devices like the TTL 7405 or 7406 Hex Invertor, which have open collector outputs. The 7406 is actually a very nice self-contained solution and most commonly used. However, if you only have one or two interrupt connection requirements on your peripheral card, and you have no other need for an inverter, then using a 14-pin hex inverter chip is rather wasteful of both space and unused inverter gates. This is the case with the Minimalist Europe Card Bus I/O card I'm currently designing. I only need a single, optional, non-maskable interrupt connection, which is driven from the positive logic output of a programmable timer. I've also no need for any additional inverters, so implementing a 7406 Hex open collector inverter just for this would be quite wasteful. My first thought was to implement a single transistor inverter using a common cheap TO92 small signal NPN transistor, but this does really require a current limiting resistor on the base connection. And although switching time is plenty fast enough, such a circuit can suffer from a slow turn-off rise time, which can limit achievable interrupt frequency. Rise time can be resolved with a second transistor and a SMIT trigger arrangement, but again we're adding more components. For this reason, I'll rule it out. The next device I'm considering is the useful SN7545 series of 8-pin dual peripheral driver chips, which I also have in my parts drawers. These compact 8-pin chips provide two TTL logic level gates with open collector driver outputs. They are good for driving up to 30 volt 300 milliamp loads, but are also just as useful as a physically smaller 7406 replacement. This would at least satisfy the goal of something smaller than a 7406, and with no additional components required, although still wasteful of a gate, as we only need one of the two available gates, but still worth having a look at for comparison purposes. Finally, there is the thought of implementing a traditional single transistor inverter, but using a cheap TO92 packaged low power MOSFET instead. This should have the benefit of not requiring any current limiting resistor on the gate input and potentially providing a faster off recovery time than a BJT solution. Of course, as usual, a simple test will tell us if this is a good option. I have some VN10K in my parts drawers, which are N-channel TO92 packaged devices, which are likely well matched to the job. So to start off with, let's look at the traditional 7406 hex inverter on our breadboard, so we can set the benchmark of how a TTL 7406 responds in the breadboard environment with an appropriate pull-up resistor. I'm going to just use the baud rate generator test circuit from my last video, which I still have on my breadboard. This will provide a good variety of square waves for testing with. As you can see, I've added the 7406 to the breadboard, hooked it up to the 307 kHz output from the baud rate generator, and a pull-up resistor on the Open Collector output on pin 2. So I've hooked up the first channel of the oscilloscope to the input, and the second channel is hooked up to the Open Collector output. On the trace you can see the input to the 7406 buffer in yellow, edge triggered on the low transition at 800 millivolts. The Open Collector output is shown on the purple trace. Interestingly, although we can see a nice fast trailing edge as the Open Collector output switches on, we are seeing a relatively slow recovery from low to high of just over 500 nanoseconds, based on a safe 2.4 volt threshold, when the Open Collector output is switched off. Now this will definitely be impacted by the additional capacitance of our breadboard circuit, but it also draws my attention to the fact that I've initially used 10k ohm resistor banks for the interrupt pull-ups on my CPU card. So this first scope trace is based on a 10k pull-up. I used 10k simply as I had plenty of these in stock, as they're commonly used as the pull-up value for more modern microcontrollers. But I do remember having the earlier thought that back in the TTL days of the 80s, a value of 4k7 was always the go-to for TTL logic family pull-ups. So let's swap out a 10k pull-up for a 4.7k just to see how it impacts the rise time. As expected, a quite significant improvement from the over 500 nanoseconds to now just over 200 nanoseconds, with double the current available and a lower voltage drop to pull the level back up when the Open Collector driver is turned off. Now I know the breadboard will be playing a part in this, but even so I'm going to revisit the CPU card schematic and update the pull-up resistor bank to specify a 4.7k instead of 10k resistor bank, even just because my past experience with TTL tells me this is the right thing to do. Okay, so with the 7406 measured as our benchmark circuit, let's now take the 7406 out of the breadboard and instead wire up an 8-pin SN75452 dual gate Open Collector driver IC. I'll stick with the 4.7k pull-up on the output on the basis that a 4.7k pull-up resistor bank is now implemented on the CPU card. Here is the schematic again of the SN75452 circuit that I drew up earlier for reference. Okay, here we have the circuit implemented on our breadboard. So let's again look at the resulting scope trace. Plug in the power. As I expected, compared to a 7406 benchmark circuit, this 8-pin option also looks to be performing well, with perhaps a rise time closer to 300 nanoseconds. Finally, let's now try out a VN10K MOSFET to see what it delivers. Once again, here is the schematic of the simple MOSFET circuit I drew up earlier. And here is our circuit implemented on our breadboard. So let's again apply power and look at the resulting scope trace. Okay, this simple single TO92 device solution is looking good. We can see a nice fast trailing edge when the FET turns on, and we are seeing a comfortable recovery time when the FET turns off, which looks fine when compared to a 7406 benchmark. It looks very similar to the SN75452 output. So in summary, I think our low power TO92 MOSFET option looks like the simple and compact retro-friendly solution I'm after for my current need of a single interrupt line driver with no requirements for any additional inverter gates in the design. However, it's also worth making a note that the 8-pin dual-line package SN75452 looks like a good option for an application that requires 2 Open Collector drivers in the design, or an application that would benefit from having a 2-input gate controlled Open Collector driving need. Right, now I think I'm ready to finalise my I/O card design and get some prototype PCBs ordered. That's it. Thanks for watching.